have resonance if what is called the applied frequency is equal to the natural frequency. The applied frequency is the frequency of the external force. So the applied frequency is the frequency of this 5 cosine omega t. That is omega over 2 pi. The natural frequency of the system is the frequency of the system without any damping. And also without any external force. And you see, it's easy to find that because if you look at the differential equation, you won't have, there's no damping here. And to see what happens when you don't have the external force, all you have is 4x double prime plus 16x equal to 0. And the auxiliary equation is 4m squared plus 16 equal to 0, or m squared plus 4 is equal to 0. So somebody tell me, what's m?
Plus or minus 2i.
Plus or minus 2i, right. So since m is plus or minus 2i, what happens is you get to the solution c1 cosine 2t plus c2 sine 2t. In other words, the natural frequency here is 2 over 2 pi. So therefore, we'll have resonance if 2 over 2 pi is omega over 2 pi, so you'll have resonance of omega is equal to 2. So omega equal to 2 should be one of the choices here, and it's choice C. Okay, so the answer to number 10 is C, 1 and 2. Pretty soon I'll have most of the answers here. That's okay. All right. Shall I tell you an easier way to do it?
Yes.
I mean, I did it this way. I didn't do it this way. I did it an easier way, and then somebody told me they were getting confused with angular frequency and the frequency which I spoke about. That's the frequency I spoke about, all right? You see, you'll have resonance when something in the particular is duplicated in the complementary. We say it resonates with what's in the complementary. So you see, what you have over here in this differential equation is the non-homogeneous part is 5 cosine omega t. So if when you look at the complementary solution, you have something that will duplicate that, you'll have resonance. So if you just look at it and you can see that the auxiliary equation over here is 4m squared plus 16 is equal to 0, so you get m is equal to plus or minus 2y. So you get the complementary c1 cosine 2t plus c2 sine 2t. When will that be duplicated? If omega is equal to 2. Done. When you take your choice, I mean, that is the way you can do it. That's the way I did it the first time in one of the sections, and the midshipman was saying, what about this stuff? Well, this is really true, and this is how I presented it, so either way it's fine. All right, let's continue this, because the next one is actually quite important. Remember, on this test, you don't have your calculator, so you can't find Laplace transforms and inverse Laplace from the calculator because you don't have that available to you in the multiple choice part of this exam. But you do have a math table. All right. So let's see what it says. If the Laplace transform of the function f of t is capital F of s, and I can hardly read that, but I'll tell you what it says. It's s over s to the 4th plus 4. So maybe I should write it down so you can see what it says. So you actually don't know the function you're taking the Laplace transform. It's just little f of t. But its Laplace transform is capital F of s, and capital F of s is s over s to the 4th plus 4. Then the question is, what is the Laplace transform of e to the minus t times little f of t? And this is what we call the first shifting theorem. Do any of you remember that? Maybe not. Okay, well, actually, if you take a look at this guy, and I'm going to allow you to have this guy or the one that the math department gives, and they're really basically the same thing as I said. I looked at it, and it's pretty much the same thing. You see, look at what L12 tells you. L12 is what we call the first shifting theorem. And what it says is the Laplace transform of e to the at is capital F of s minus a. Capital F is the Laplace transform of little f of t. So you take the Laplace transform of little f of t and you replace s wherever you have it by s minus a. That's what you do if you have e to the at f of t. What if you have e to the minus at f of t? Well, then you replace s by s minus a minus a, or s plus a. Okay? So over here, by L12, you got the Laplace of e to the minus t f of t. So somebody tell me, that's going to be capital F of what? S plus 1, exactly. So what it means is wherever you have s gets replaced by s plus 1. So you get s plus 1 over s plus 1 to the 4 plus 4. So what we do is we take a look and see at what the choices are, and hopefully that's one of the choices. I think it is, but let's see. So we're doing 11. And this is out right away, because this is a function of t. If you take the Laplace transform, you get a function of s. So we can throw that away right away. But b looks like the right answer. S plus 1 over s plus 1 to the 4th is right. The other two are just not right. So the answer to 11 is b, as I've shown. Okay, so one more, guys. Let me get up to number 12, because that's where I got up to in the other classes. All right. So number 12 says you've got to find the inverse Laplace of this fraction. If you have a fraction like this, what you'd like to do is you'd like to factor the denominator. But the question is, can you factor the denominator? No. What about b squared minus 4ac? It's negative, so you can't factor the denominator if you want real factors, and you want real factors. So you can't factor the denominator, and you can't just put it in the calculator and hit inverse Laplace because you don't have a calculator. Does anybody remember what you got to do? What? You got to complete the square. That's exactly right. That's what you got to do. So here's how you complete the square. S squared plus 4s plus 8. So you take half of the coefficient of the linear term, so half of 4 is 2, and you add it on squared. So you add 4. But if you add 4, you got to subtract 4 to make it, to compensate for it. So what you get is the denominator here is you get s plus 2 quantity squared plus 4. This is s plus 2 squared, and that's 4. Now, do you also remember that on the top over here we have s plus 3? But we want to make this thing a function of s plus 2. What it means is wherever we see s, what do we want to see? We don't want to see s. What do we want to see? We want to see s plus 2. So what we do is we change that s to s plus 2. So we've added 2, and again, we have to compensate for it, so we subtract. And now this thing is a function of s plus 2. And now what I do to find the inverse Laplace transform is very easy. So this is going to be the inverse of s plus 2 over s plus 2 squared plus 4 plus the inverse of 1 over the same thing. And now I actually have a choice from my table. I could either use L12, or I guess it's L33 and L32, but since I used L12 before, let me use L12 again. In particular, you see I have this and I have this, right? L12 tells me if I have a shifted transform, the inverse of capital F of s minus a is e to the at times f of t. If I had capital F of s plus a, the inverse would be e to the minus at times the inverse of the unshifted transform, right? So by L12, what this becomes is the following. I have s plus 2 here. So it's e to the minus 2t times the inverse Laplace transform of s over s squared plus 4. Anybody tell me what's the inverse Laplace transform of s over s squared plus 4? It's cosine 2t. Cosine 2t. Again, by L12, the inverse of this is e to the minus 2t times the inverse of 1 over s squared plus 4. All right? But the inverse of 1 over s squared plus 4, remember, with sine, The Laplace transform of sine omega t is omega over s squared plus omega squared. So what do I need up there? I need a 2. So I multiply and divide by 2, and I get a half there times the sine of 2t. And therefore, that is the inverse Laplace transform. What I'm saying is you could have used L12, just as long as you complete the square, you could have also come through with L32 and L33. And the answer to this, let's just make sure we got an answer. This was number 12, and let's just see. So this is not the answer, that's not the answer, but the answer is C. So the answer to number 12 is C. And I think with that, I will stop. Where is my section leader? Mr. Lawrence? It was a pleasure teaching you people. I hope that you enjoyed it as much as I did. And this has been almost 40 years for me.